Hi, this is Mr. Bissonette with another episode of Math in the Classroom. Today we're going to work on solving systems of linear equations. So our learning target is going to be I can solve systems of linear equations. Okay, so when I'm teaching this to students, first I kind of tend to define this. What does systems mean? This means two or more. Okay, and linear equations. What are our linear equations? They're in the form y equals mx plus b, or a lot of times when we're working with these we'll see ax plus by equals c. Now again, I like to teach this with the big picture, start out there. What we're doing is we're graphing two lines. Now there's three different options that could happen when we graph these two lines. One option, our normal one that we see a lot of times, is they're going to intersect or they're going to cross. How many times do they cross? Here they cross once, so there's going to be one solution. Okay, what that might look like when we solve this down is we might get something like x equals 3, x equals -8, or something like that. Another option that can happen is we can have these lines be parallel. These are the two that students tend to get. Okay, parallel lines. And I ask the students, how many times do these cross? They do not cross. So there's going to be no solutions. Now I'm really careful to emphasize that. Do they cross? No, they do not cross. Sometimes students will try to say there's 0 solutions, but being really picky with our math, x equals 0, 0 could be a solution, so I like to try to really define that crystal clear. That way students don't get that mixed up at all. So here they do not cross, so there's no solutions. And x equals 0, that could be a single solution. So we try to keep those very distinct. All right, when we solve it down, what might that look like? Well, it's something that is not true. So we get something like 8 equals 7. It's not true. 8 does not equal 7. Or 4 equals -5. Okay, not true. 4 does not equal -5. The third one that students miss a lot of times, this is the tricky one, but it's the case where we have a line over the top of another line. They coincide is the mathematical term for this. And again, once we get that there's two lines on top of each other, how many times do these lines cross? Students will a lot of times say they always cross. Mathematically, what does that mean? Infinite solutions. When we solve this down, what does that look like? This is going to be a true statement, so maybe something like x equals x, or maybe you'll finish with something 4 equals 4, something that is true. Okay? So systems of linear equations, what are we doing? A lot of times we're finding that intersection point, but we have to also know that there's a couple other options that can happen when we're trying to solve these. Okay, so there's the big picture. Now zooming back in. A lot of times we will start off with something like this where we have y equals 4x minus 9, and then we'll have another one where it says y equals x minus 3. Okay, I like to kind of go above and beyond when I'm teaching this, and I show students this kind of deal, a thing in philosophy. It's called a tautology. Essentially, it's a truth statement. Now, a way that the truth statement works is if we say 100 pennies equals 4 quarters, and 4 quarters equals $1. Since that is a truth statement all the way through, we can say 100 pennies equals the $1. Why do we say that? Well, notice 4x minus 9, what does that equal? Y. But what else does y equal? Y also equals x minus 3. Okay, so if this equals that, and that equals what we have over here, then we can say that this equals what we have over here. And that's that tautology, that's that true statement. So we have 4x minus 9 equals x minus 3. Once we have this, this is a pretty standard system of linear equations. The way that I always teach it is we're undoing PEMDAS. So we're going the reverse of, I want to identify my variable side. Variable side tends to be the side that has the most variables to start off with. So that means this side is going to be my number side. Alright, from there I start moving things and I start with my adding and subtracting. So number side, so I move variables over here. I have a positive x. What's the opposite of a positive x? Minus x. What I do to one side, I have to do to the other to maintain that equality or that equalness. So we have 3x minus 9 equals negative 3. Now, I have a number over here, so I'm going to move that to the other side. Still working with my adding and subtracting first. So what's the opposite of minus 9? Plus 9. So we're going to have 3x equals negative 3 plus 9, which is going to be 6. No more adding and subtracting, so now we move on to our multiplying and dividing. What's that 3 doing to the x? 3 times x, opposite of multiplying by 3, is dividing by 3. So we get x equals, and this is one of those simple little things, dividing by 3, as early as I can get students using that fraction bar instead of the division side. I think as they move further on into mathematics, that will really help them. But just a small little detail. 6 divided by our 3 is going to be 2. Now, if it is asking for the point of intersection, okay, then we have to get both values. Currently, we only have the x value, so we plug it into either one of our equations to get our y value. So y equals, x equals 2, so 2 minus 3, so our y is going to equal negative 1. If it's asking for the point of intersection, we're going to put it in point 4, so we'd have 2 comma negative 1. And you can pick either equation when you are plugging that in. Okay? Feel free to pause this if you need to take another look at the notes. We're going to go through one more example, and then we will go from there. So pause it if you need to take a look. If not, we're going to go on to the next example. Okay, we're still going to go for the point of intersection on this next one. We're still going to have to use the reverse of that PEMDAS to solve, but it's going to be a little bit different as we go. Alright, so the next example, we might have something like 7x plus 2y equals negative 19, and negative x plus 2y equals 21. Okay, this is where those linear equations are now in standard form. They look different, but we still just have two lines. We're trying to figure out if they cross, if they're parallel, or if they coincide. What I like to identify is the terms that are similar, okay? When I mean similar is it could be a 2y and it could be a negative 2y, or a 3x and a negative 3x, or a 4x and a 4x. They can be the same, or they can just be opposites of each other. Right here, these are the ones that are going to be the same. The next thing I ask myself is, what would I do to get them to sum to 0? In this case, we're going to subtract these. So what we do there, we do through the entire system of equations. So we'd have 7x minus negative x. Be careful, that minus minus is going to turn into a plus, and we would get 8x. And then I'd have negative 19 minus 21, so we're going to end up with negative 40. From here, we're undoing our PEMDAS. We are multiplying by 8, so the opposite of that is going to be dividing by 8, and we're going to get x equals negative 5. Now again, if we're going for that point of intersection, we have to plug that in. I would probably pick the bottom one just because it might be a little easier. So I'm going to have negative 5 plus 2y equals 21. Minus minus is going to become a plus. Okay, we're going to subtract our 5 from both sides. So we're going to have 2y equals 16. And then 2 is multiplying the y, so the opposite is going to be to divide both sides by 2 to get y equals 8. So the point of intersection for this one is going to be -5, 8. Now sometimes with these, you might not have ones that match up. If you don't have something that matches up, you can multiply the whole equation by a number to get it to work, and then once you have that, then it's the same deal. All right, again, that's solving systems of linear equations with Mr. Bissonette. Thank you.